the point of this series is to talk about the routes of transmission by which infections can be passed on around the world. And there are broadly 5. And every infectious disease has got a dominant route by which it's passed on, and it may have a secondary route as well. But it doesn't change that route or those routes. They remain the same, even if usually you jump species. So, for example, at the moment we are dealing with coronavirus, a respiratory virus has jumped from bats. It almost certainly was a respiratory virus previously, it's a respiratory virus now. Monkey viruses that are sexually transmitted become human viruses that are sexually transmitted, and so on. So the route of transmission is extremely heavily conserved. And the 5 routes, and the 5 lectures I'll be giving cover each of these, are vector-borne, which are primarily insects, but also there are other vectors, arachnids like ticks, food and water, things you eat or drink, sexual and blood-borne, respiratory, touch, where you actually pass on the infection by touching someone. And with all of these, there is generally a dominant and then sometimes a secondary or even 2 secondary routes, but one route is dominant. And why this is really critical is if you know the route of transmission, you can predict how it's going to behave, and you can also intervene. So the route of transmission tells you both about the disease and about its control. So that's why this is important. Next slide, please. So many diseases that we have are largely or entirely vector-borne. And the vector-borne diseases are the ones I put up here. An important disease, for example, that I'll just talk about historically is plague, which is a disease that had a route where it was transmitted by fleas, as I think most people in the audience will know, but also had a respiratory route. So that's an example of a disease that had 2 major routes of transmission. But most of the infections that I'll be talking about today have only got a single route of transmission, and that is via the vector, the insect or arachnid that passes it on. So malaria, for example, passed on by Anopheles mosquitoes. I'll talk quite a lot about that because it's probably the best example of a vector-borne disease and the most important one. Dengue, Zika and yellow fever passed on by different mosquitoes, so the exact species really matters. It's not going to be something that the infection generally can pass between different species. Sleeping sickness, river blindness. I'll go through several of these over the course of the lecture. The point I'm making with this slide, however, is that very many insects and arachnids can pass on infections. Each one of those can pass on one or a few infections. And if you know where that insect lives, if you know what that insect does, that predicts what the disease will do, and it also tells you where you can intervene to stop the infection. So large numbers of potential routes. Next slide, please. Now, the vector-borne diseases that we have require different control measures from other transmission measures. Making it much harder to deal with vector-borne infectious diseases is that they are often extremely efficient at transmission. I'm going to take the example of malaria. Now, most people are now very used to the concept of R. This was very important when we were talking in the early phases of the pandemic for COVID, and we talked about an R of 1 or 2 or 3. For malaria, in parts of Africa, the equivalent of R for vectorial capacity, which is equivalent of R, is over 100. So vectors can be extraordinarily efficient transmitters of disease. The second thing which is different about them is that you do not need to meet the person who's infected you or the animal who's infected you. They could be a village away, and the insect can fly between the 2 of you and pass on the disease. So it's very good at passing on infections over space. And some insects can actually travel extremely long distances, either because they want to eat you, because they've smelt you, or indeed some of them actually go up on the winds and can be traveled very long distances, in some cases hundreds of miles, taking an infection from one place to another place. So they can do things over space, and they can also do things over time. There are some infections, and I'll give an example here of the chigger mite, which is tiny. This is actually literally on the head of a pin, this chigger mite. But this infection, one infection on that, something called scrub typhus, can be passed on mother to daughter through generations, so that actually it gets infected from a human at one point in time and can infect a human several generations later. So vector-borne diseases are actually a very good way, if you're an infection, of being passed on from one person to another. So that's, in a sense, in favour of the infection. Making it easier for us, the humans, is firstly that vectors tend to have a very specific geographical distribution. And that's because the insects don't live under all environments. Sometimes that's just because, for example, they prefer rural areas to urban areas, but very many of them only live in a particular part of the world or a particular climate environment. You will not get an infection outside that environment. You'll only catch it in those environments. So that geographical concentration is important. And the final thing is, if you've got a disease that is passed on largely or entirely by a vector, if you can kill that vector, you stop the transmission and therefore you stop the disease. And that's one of the key things in understanding how you control a vector-borne disease, quite different from all the other disease types I'll be talking about, which tend to be directly or indirectly human to human. You've got this thing in the middle, the vector, and if you can kill the vector, that will lead to an improved outcome. Next slide, please. In the UK, vector-borne epidemics, large-scale outbreaks of disease, have gone for now, but when this college, Gresham College, was founded, these epidemics of vector-borne diseases were in fact very common. And some serious ones that would have been around when the first Gresham Professor of Physics was lecturing included plague, epidemic typhus due to body lice, I'll talk about both of these, and malaria, which was endemic in the UK. Last case transmitted within the UK was in the 1920s. Until then, we had malaria in the UK. The UK currently has relatively few vectors with epidemic potential. That is to say, they can actually cause a big outbreak. Ticks, arguably, and midges. There are animal midge diseases, but not human midge diseases. But if we ever got a human midge disease, that would be a potential risk in some parts of the country. But global warming could change this. Not next year or the year after that, but at some point in the foreseeable future, if temperatures go up, various vectors will move up away from their current heartlands into slightly warmer climates, and we could therefore get transmission, which we cannot currently do. So this is an area where global warming could potentially change things in the interests of the infection. On the right, what I've shown actually is a picture from a book demonstrating the two phases of malaria, as it was then called AU fever, or marsh fever, the hot sweating stage and the cold shivery stage, which alternate with malaria. So this is just a rather good representation of that disease. As I say, common in large parts of the UK, mainly in southern and eastern England. Next slide, please. So a couple of diseases that still exist, they still infect people, but they are historically much more important than they are now. And then I'll turn to a number of diseases that are much more common now. And the reason I'm making that point is we have been very successful through science and development at dealing with some of these major epidemic diseases. The first one has to be plague. Plague, the absolutely archetypal, devastating epidemic, reduced the world population, as you can see, by a very substantial amount in the 14th century, where the plague epidemics reduced the European population by somewhere between 30 and 60%. So a quite astonishing epidemic. The Great Plague of London, which was after this college was founded, the official record had over 68,000 people dying. Almost certainly that was more than that, out of a total population at that stage of just under 500,000. So this was a really substantial risk. The risk of a plague epidemic now is zero. There are still cases, indeed there are still outbreaks. And the reason for that is partly development, but partly because we've got treatment in the form of antibiotics, which we can use as part of treatment. Next slide, please. So looking at plague as an example, and the reason I'm using plague, because with all of these I'm trying to make general points as well as the specific points. Plague is an example of a disease which is passed on both by vectors and by another route. In the case of plague, it is by the respiratory route. And plague was the reservoir, is various forms of mammals, of which the most important in Europe were rats, black rats. These rather friendly-looking creatures up there on the right. And on them they had fleas, not to scale, incidentally. The rat would probably have noticed that, but that's the flea blown up. The fleas, the rats had the plague, the fleas bit the rats, and then the fleas jumped off onto humans, particularly if the rats were dying, bit the humans, and that gave bubonic plague. That is, it bit the arms or the legs of the person, and what they got is it tracked up to their lymph nodes, which is up here. This photo in the bottom is someone with plague, bubonic plague, causing these lymph node problems. That's bubonic plague. Then sometimes it goes into the blood, that's septicemic plague, and sometimes the blood form went into the lungs, causing what's called a secondary pneumonia. Now, if someone with that plague then coughed over someone, then that would pass it on respiratorily, and then they would get a primary pneumonic plague, and then they would pass it on person to person as a respiratory infection. So here's an infection that's passed on by two routes, the vector route and the respiratory route. Next slide, please. Another historically very important infection was epidemic typhus and trench fever, which is a rather milder disease, both passed on by body lice. And just to be clear, body lice are not the same as head lice, which are very common in children. Head lice are completely different and not a risk for this. It's very common in crowded and limited hygienic settings. So classic examples are wars, refugee camps, and jails. Jail fever was one of the well-known ways in which this was described. This has a fatality rate of around 10%. So it's passed on in crowded environments with people with lice. Lots of people would catch it, 10% mortality. So it's a lot more, for example, than we have with COVID for most people who are younger at the moment. So significant disease. Another one passed on, something called trench fever. It infected a large number of well-known writers you'll have heard of, for example. Less severe, but can be very prolonged, can go on for very long periods. This was something which we now don't see except in very specific settings because of two things: hot washing of clothes, which kills the lice, and DDT. As you can see, this kind of what looks like a deodorant is in fact DDT being put in to try and kill lice who are living in the hems of this soldier's uniform. Next slide, please. So those are some diseases of historic importance, still occur. In case of plague, Madagascar has a lot of plague, but there's plague in various other places, but not a chance of major epidemics and jail fever of different sorts. What we do have with us is malaria. And I'm going to talk quite a lot about malaria because it's mainly as an example of the absolutely classic vector-borne disease. Very important anywhere where you can actually have it transmitted by the mosquitoes, Anopheles mosquitoes. It was much more widely distributed than it is now, and I'll come on to why that has changed. Well known from ancient times. Used to be very common all the way up the seaboards of the USA, all the way across Europe, including the USA, including the UK, in particular in southern Europe, northern parts of Australia, all places it now has gone from. But this was its natural range. And it initially had a significant reduction over time because of land use change. So in the UK, for example, the draining in the marshes in the east of England led to a significant reduction in malaria. People weren't doing it to achieve that, but because people drained them to have agricultural land, that led to the local vectors, the local Anopheles species, not having a base, and there was less agricultural living, and that led to malaria gradually dying out. But as I say, the last case in the UK was in the 1920s in southern England. Next slide, please. But that was accidental in a sense. What we have now been able to do is deliberately to take on this very major cause of mortality in children and adults, particularly now in children. And the key to this was the discovery of the life cycle of malaria, which is one of the great breakthroughs in medicine, and for which Sir Ronald Ross received the second Nobel Prize for Medicine quite recently, although many other people were involved in it. He was a strange, difficult, but brilliant man. I'll come back to him. And what he discovered, along with others, but he was really the person who finally discovered this, is when the female Anopheles mosquitoes, the males are completely harmless, don't worry about them. When the females suck up blood, which they have to do to actually be able to produce their eggs, which they usually do usually every 3 days, varies on the species slightly. They suck up the sexual forms of the parasite. It then matures in the gut of the mosquito. That's important. So they can't fly to the next person and then bite them and pass it on. It's got to go through a long period of several days. That's really critical to how we control it, before it then can pass it on to someone it bites. But from then on, anyone it bites, it could pass on malaria parasites. And as I say, hugely efficient at transmission. Next slide. Sorry, before I go on to that slide, what you can actually see is that on the right, we've got the Anopheles mosquito. Then down on the right is the form maturing in the gut of the mosquito. This is what Ronald Ross saw down his microscope. On the left are the malaria parasites, and on the top side is the sexual form of parasites. That is the malaria life cycle that Ronald Ross discovered. Now, because it's transmitted by a mosquito, the transmission of malaria is extremely variable, depending on where you are. And I've just taken 3 photographs from near where I used to do quite a bit of my work, in Tanzania, and they're all within 3 hours of one another by road, if you drive slowly. On the left is down on the coast. In that area, warm, humid area, the average child at that stage caught malaria 4 or 5 times a year. Incredibly common. If you drove up towards Kilimanjaro, which you can see here, up on the slopes where the coffee plantations were, no malaria. It was too cold for the mosquitoes. And if you were down in the valley, there was a bit of malaria. The average person might get every 2 or 3 years, but it was still cold, and therefore the mosquitoes were not efficient at transmitting in that environment. If you drove to Dar es Salaam, also on the coast, but it was far too built up for lots of mosquitoes. Those kind of species don't like the urban environment, and therefore much less malaria because it's urban. So you could explain why people got malaria from where they were, because the mosquitoes will only live effectively in certain areas. And in some of the species, in Asia, for example, even more specific about where they will live. Most Asian species will not live anywhere near any large or even moderately sized town. They'll only live in rural areas. So it varies over space, over quite short space. It also varies over time. And because the rains in most places are very seasonal, the UK is exceptional in that sense, but they've got very seasonal, the mosquitoes will only tend to be there in large numbers during the rainy season, the monsoon season around the world. And that usually is in very highly seasonal areas, only for a few months. So this is Nigeria, the north of Nigeria, where this very distinguished emir is from. And in the south of Nigeria, where it's very hot and swampy, there's malaria all the way through the year. But if you go right up to the north, which is bordering on the Sahara, the rains only come for 2 or 3 months of the year. And that's the time there's incredibly intense malaria transmission. And then it dies away again for several more months. So malaria will vary by both space and time because the mosquito vectors will only live in certain environments. So understanding the environment makes a big difference to the transmission. Now, this is the only bit of maths I'm going to do in this entire year, you'll be pleased to hear. And this, for those of you who've read far too much about it for pleasure in the last 2 years, is a mathematical model. It's a simplified version of one, but it is one. This is one of the simplest and, in my view, most powerful mathematical models. And I'm going to walk you through it. And if at the end of it you understand it, you'll understand everything about malaria. And if you don't understand it, you'll understand most things. But it's just useful to have a go. This is the other great contribution of Ronald Ross to malaria. This is Ronald Ross on the right with his rather fine moustaches. He found that the vectorial, and he did this, subsequently it was developed by a gentleman called MacDonald, so it's called the MacDonald-Ross equation. The vectorial capacity, which is equivalent to R, if you're a vector-borne disease, equivalent to R, where one is one person gives it to one person and so on, is proportional to M, which is the density of mosquitoes. Simple. Twice as many mosquitoes, twice as much malaria. That's not particularly tricky. So if you can halve the number of mosquitoes, you'll halve the amount of malaria, or at least the transmission of malaria. The next one, slightly more complicated, person biting habit, anthrophily. A is squared, and that is because to actually pass on malaria, this has got to bite one person to catch it and the next person to pass it on. So the more likely it is to bite a human, the more likely it is to transmit, and because it's got to bite a person to catch it and a person to pass it on, that's squared. That therefore means that the mosquito vectors that take the majority, let's say you take twice as many of your meals from a human compared to a chicken or a lizard or a cow, that makes you 4 times as likely to pass on malaria. And some mosquito species take almost all of their meals from humans, some take only a few. And if they only take a few, they're much less likely to be efficient as transmitters of malaria. But the third one is really the most important one. The probability that a mosquito will survive a whole day is P to the power of N, which is the number of days between biting someone to become infected and being able to become infectious, which is 9 to 11 days later. Which, if you can remember back to your O-level or GCE or equivalent mathematics, something to the power of 9 is a huge multiplication factor. So just a small reduction in the chance that a mosquito will live a whole day from the time it's bitten a human can lead to a massive reduction in its transmission. This was the really brilliant insight of Ross. The other two are interesting, but that one was a really brilliant insight, and I'll show you why. Because if you know this, you can do several things to actually deal with the mosquito. The first thing you can do is you can remove their breeding sites. And that's the way that malaria went away in quite large parts of the world, including in the UK. Drain the swamps, that's where the only place where the mosquitoes will live. If you take away their breeding sites, they're gone. But some mosquito species will breed absolutely anywhere, in a hoof print, in a tyre, in a gutter, in a sewer. The second thing you can do is kill them as larvae. So you know where they breed, you can't get rid of those places, but you can put oil on the top, you can put fish in that eat them, you can put in chemicals. There are a variety of ways you can try and basically destroy them. And this is the Richard III approach, basically, to trying to deal with this. You get rid of them when they're too young to cause you trouble. And there are places where the transmission is low, where that is relatively effective. But if the transmission is 100, which it is, as I say, in parts of Africa, then a small reduction is not going to be enough to get on top of it. You can kill them before they bite a human. You can put in bed nets that are insecticide treated, and they are effective to some degree. But the key thing which Ross learned, and from his mathematics, was if you can kill them after they've bitten a human, and you've got several attempts at it because you've got 9 days before they're going to become infectious, it's to the power of a huge amount. You're going to really reduce the transmission if you're going to reduce the probability of that mosquito surviving any longer. And why that's important is that because most mosquito species will come in, most Anopheles mosquitoes, they'll come in, they'll bite you, and then they'll go on a wall to digest their food. And therefore, if you can put insecticide on that wall, you're not going to protect the person who's been bitten because it flies in through the window, it comes and bites them, but it'll then rest on the wall, gets DDT, which is the key insecticide they were using, dies, or if it doesn't die, it'll happen the next time, and that they're dead before they get to the point they pass things on. That was the key understanding that Ross had. And using this very powerful insight, therefore, with huge power of mathematics, because of the power of 9, he actually was able to say, right, what we need to do is, therefore, people subsequent to him were able to say, right, what we need to do is kill these mosquitoes after they've bitten. We know where they are. Much easier to find them because they've gone to you. And that way, we're going to bring malaria rates right down. And that's what happened. We started having large numbers of people trained to spray walls with insecticide, as on the left. And then more recently, what we've used is insecticide-treated bed nets, which means that they can kill them on the way in. They protect the children underneath it, but they also kill them on the way out meaning they protect subsequently other people. So here are two very effective ways of killing mosquitoes at the point you want them, which is on the way in, on the way out for humans. So with that, we thought, well, we've got a fantastic insecticide, we know what we're doing, we've got the mathematics, let's eradicate malaria. Great idea. And there was a malaria eradication attempt, a very serious one, led by the World Health Organization, which went on all the way through up to the mid-70s. So from just after the war, when there was a very strong feeling, if we put our collective effort together, we can actually get on top of this really major infection. There was an attempt to eradicate two diseases, malaria and smallpox, one of which was achieved, one of which, as I'll come on to, was a partial success. So the malaria distribution in 1948, before this eradication attempt using DDT was brought in, is on the left, very significant transmission, including Europe, including USA, including northern Australia. On the right, and these are contemporaneous maps, on the right what you can see is where malaria had got to at the end of that eradication attempt. It didn't succeed, but it achieved in really pushing it down into its heartlands by this process of actually killing mosquitoes after they'd bitten a human. And therefore, that's accelerated a natural process by which malaria used to be endemic everywhere in the world, and it is now extremely rare outside the tropical zone of parts of Latin America, Africa, and Asia. And in fact, it's been pushed largely down into its heartlands, most of which are in Africa, particularly West Africa, and a little bit some patches of Asia. And those Asian patches are getting smaller. And this is the current malaria approximate range. Darker colours means more malaria. But as you can say, it's gone from many of the areas where previously it was by these simple techniques, focused on the vector, focused on killing the mosquito. Now, vector, obviously with all diseases, you don't just want to kill the vectors because some people will catch the disease. And in the case of malaria, the two other things you can do with all diseases, you can think about prevention with vaccines, come on to that with malaria, important for some diseases, but the key one for malaria was treatment. And so if people get malaria, you can treat it very effectively if you catch people early enough. That's both good for them, it stops them from dying, that's the principal aim, but it also means they're less likely to transmit onwards. And we went through a cycle of some very important chemical drugs, but we're now back to the mainstay of malaria control is two drugs that have been around for hundreds of years. On the left, quinine, which originally came from Latin America, traditional medicine, and on the right, Artemisia annua, sweet wormwood, been used in traditional medical practice in the UK for hundreds of years, but this understanding of it came from China. This is from Chinese traditional medicine, been around for at least 1,000 years. So the cutting edge of malaria treatment remains two old drugs based on plants, been around for centuries. Very effective drugs. And the combination of effective treatment and effective anti-malarial activity via bed nets, insecticide-treated bed nets, has led to a really remarkable reduction in malaria mortality over the last 20 years. So at the turn of the century, the mortality rate in children was over 700,000 deaths a year, well, children and adults, but most of them are children. By 2019, that was down to around 400,000. That is an astonishing achievement of medical science, and that's basically the combination of insecticide-treated bed nets, some spraying of walls, and some drugs which are essentially old drugs that have been repurposed for this reason. A great achievement. Over this period, probably 7.6 million malaria deaths have been averted using these relatively simple techniques. Now, we don't have malaria endemic in the UK at the moment, although there are mosquitoes that, in theory, could pass it on. There are certainly a lot that could pass it on in southern Europe. But we do sometimes have malaria cases in the UK. And I just want to make this point because many of you may travel to places where malaria is common. Malaria remains a very significant risk to travellers if they go to endemic areas. And I think the thing which people underestimate when they say, oh, I don't really need drugs, is that this is a potentially fatal disease which the average person may get 4 or 5 times a year. This is more common than flu in the UK. And if you don't, therefore, protect yourself by sleeping under insecticide-treated bed nets or by taking prophylaxis, and preferably both, the chance of getting malaria is actually very high. It's not a small probability, it's actually a very high probability. So it is really worth doing. In the UK, we usually run somewhere between 1,500 and 2,000 cases a year imported. Almost all of those are people who've not taken any prophylaxis. So these were preventable cases. So if I'd been giving this talk 2 weeks ago, I would have stopped it at that point. But last week, after decades of research, the World Health Organization recommended that we deploy a malaria vaccine, the RTSS malaria vaccine. It's been being deployed over a period of time. This is a substantial step forward. It is a vaccine which, and it's important to understand what it does do and what it doesn't do. What it does do is it does reduce by around 30%, this is the WHO figure, at least for a period of time, not necessarily for a long period of time, but for a period of time, probably some years, a reduction against severe malaria. Now, that sounds like a small amount. We're used to thinking about vaccines, for example, COVID, by 90% or more. But if you've got an incredibly common disease with a high mortality rate, then a 30% reduction is a really worthwhile thing to have. But it's got to be layered on top of other things. So we still have to attack the vectors, we still have to give the drug treatment, but now we have a third pillar, which is malaria vaccines, as of, say, last week. So this is another important step forward in this really important disease of particularly childhood. Now, I've talked a lot about malaria because I wanted to use that as a way of laying out the principles. So I'm now going to talk in much shorter time about a variety of other vector-borne diseases. But I think to understand the range of diseases that you can get. And the first one I want to talk about is another one passed on primarily in Africa and Asia. It's another parasite like malaria. It's a worm. And it's a worm that's passed on from your blood to someone else's blood. Same basic way it's passed on as malaria is. And what it causes is inflammation of the lymphatics, which is the drainage system of your appendages, your arms, your legs, in women, breasts, in men, genitals. And it can lead to this extraordinary and very debilitating swelling of the legs. This is an old photograph, but there are still people who have got conditions like this. So this is definitely something you want to get rid of. Very much like malaria, the two pillars of control are you treat, you kill the mosquitoes. Very similar processes, actually, reasonably similar mosquitoes in many ways. But the other thing we use for this one is mass drug administration, where people are given, everyone in a village will be given drugs at the same time. And the drugs are there to kill the baby worms so that then if a mosquito bites someone, there's nothing to transmit. And that combination has led to a very significant improvement in Africa and Asia where this disease is common. So it is now very much rarer to see people with such advanced disease. And in fact, many fewer people have got lymphatic filariasis, and a few countries have already eliminated this disease, again, by a combination of vector control, mass drug administration. That's the key to getting on top of this disease. Then I'm now going to move over to a group, those are diseases passed on, those are parasitic diseases passed on by mosquitoes. Now for some viral diseases passed on by mosquitoes. And this is a different mosquito species completely. This is the Aedes mosquito. There are two different, it's a genus of different ones, two different important ones. Aedes aegypti and Aedes albopictus, doesn't really matter. Elegant mosquitoes, as you can see, lyre-like thing on the front, nice stripy legs, have a bite like a Black & Decker drill. You really know about it, tend to go for you at sundowner time. They pass on several very significant and important diseases. Dengue fever, Zika, I'll talk about those two. Chikungunya, which is an unpleasant disease, can cause rheumatological disease, rheumatic problems, and yellow fever. Yellow fever is much less of a problem than it used to be because there's a very good vaccine against it. But for the other three are still significant issues. And Aedes has a big disadvantage from our point of view, compared to other diseases. He's very well adapted to peri-urban living. So unlike the mosquitoes I was talking about previously that generally don't like cities, Aedes loves cities. It's a city slicker. It also is a daytime feeder. And therefore, bed nets and things like that, which concentrate on protecting people at night, are not going to have any advantage. And people, of course, have to go about their daily business, and you don't have that ability to say, well, this is where people are going to be bitten. It's currently mainly in the tropical zones, the isotherms, 10-degree isotherms. It's to do with temperature and rainfall primarily. But it's spreading. So Aedes is now really well adapted to the peri-urban areas around the world. So this is to give an example in Latin America, where Aedes transmitted infections have gradually increased. On the left is where they got to in the 1980s. In the middle is where they got to in the 1990s. And on the right is where they got to in the early 2000s. So this is unlike malaria and lymphatic filariasis. Things are getting better. We know how to interrupt this. We've got very effective strategies. Here things are actually getting worse. And dengue, for example, can be an extremely unpleasant disease. You get hemorrhagic fever in some people, or a shock syndrome, a slightly different approach. These are life-threatening if not properly treated. And the symptoms for some people, they may not get severe disease, thank you very much, but they also can lead to very prolonged symptoms where people can feel the so-called dengue blues were well known well before post-viral fatigue was more widely known. It was a well-recognised phenomenon. You get dengue and you feel really tired for months afterwards. Producing a vaccine has proved difficult. There are vaccines available, but they should only be used in people who previously had an infection. If you use them in other environments, you can actually make things worse. So currently, we don't have a good vaccine for mass use in most situations. So that's dengue. We do need to get a vaccine because controlling this, as I'll come on to, is tricky. The second Aedes-transmitted infection, which all of you will remember from relatively recently, was Zika. Zika appeared to come out of nowhere. We had a huge epidemic in Brazil in the same year as Brazil was hosting the Rio Olympics. So I think the eyes of the world were on this. And it caused this terrible situation where mothers, relatively trivial infection generally for the mothers, a few people got severe disease, but quite a lot of mothers women would have babies who had very small heads and are likely to have significant neurological damage. And you can see along here, these are the years from 2010 through to 2015, the number of cases of this, and then suddenly Zika appears, massive numbers of children born with these very small heads as a result of the infection. Now, this big epidemic of Zika, which was passed on by Aedes, it's not because this is a new disease. This was first described in the 1940s in Uganda, and then it went by a route carried by humans, by aircraft. It basically hitchhiked all the way across to Asia, then across the Pacific, stopped off in French Polynesia, and then into Latin America. And it wasn't really till we got to Latin America that there was this explosive outbreak of Zika. The infections that can be passed on here, the mosquitoes are everywhere in the world. Zika is still around everywhere in the world in the tropics. So I do expect there to be further, I'm afraid, outbreaks of Zika over the next few years. We don't know when. It disappeared for quite a long period, but the chances are it will at some point be back. And it's very important we now get a Zika vaccine, particularly for women, before they actually become pregnant. That really is the key group to vaccinate. And we think of these as tropical diseases, but there is actually the potential for spread over quite a significant range. So what we have is two Aedes species. The Aedes aegypti on the left is a more efficient vector, and that's got a relatively distinct transmission rate. Everywhere there's red, you'll get Aedes. But as you can see, it goes right up into the USA, goes up into South Asia, a little bit in southern Europe. But on the right is another species, Aedes albopictus, and that has a much wider distribution, including much of southern Europe. It's a less efficient vector, but it's moving around the world. And it's moving around primarily on or in, particularly in, tyres. So the tyre trade is massive, and you've got water in nice warm puddles inside this, and the mosquitoes pass on. Also, the thing with this is that its eggs can overwinter, which the one on the left can't. And therefore, it can deal with colder environments, which the one on the left can't. And so Aedes albopictus is moving up in Europe, and therefore Aedes-associated infections are becoming a greater risk in southern Europe, and if global warming were to continue, it will gradually move further up Europe. Just as in, for example, malaria actually is gradually moving up mountains due to global warming, it can go a little bit higher every few years because the temperature is a bit higher overall. So climate change is going to extend the range of these mosquitoes and therefore potentially extend the range of these infections. And this is a problem because controlling the Aedes is not easy. They are tough, they're tough opponents. They live in very small water sources. You can do conventional, moderately effective things. They include covering water sources. You don't want to have water pots and pans, screens on doors and windows, fogging with insecticide, environmentally not a good idea. But if you've got a big epidemic, you do actually, from time to time, that you do have to do it. It's not hugely efficient, very environmentally, potentially damaging. There are a whole variety of experimental methods by which we could interrupt them, and I'll just talk about 3 of them. One of them is a technique where you breed males to be sterile, and the males mate with the females, and they only do it once, and the females think, great, I'm in business now, but the males, they weren't doing it because they're sterile, they've been radiated, whatever it might be, and then you get a collapse in the population. That's one theoretical way of doing it. Second way is genetically modified mosquitoes. And there are a variety of very, very clever mechanisms to try and change the genetics of them, which actually will lead to genetic collapse. Now, there's a lot of nervousness about this, because once you release genetically modified mosquitoes into the environment, you can't pull that back necessarily. So this is something which we're doing a lot of debate around how best to deploy these. But in theory, this could be one of the mechanisms for this really difficult to control mosquito. And a third example of the ways you can control them is to infect them with Wolbachia, which is an infection which makes them much less easy to transmit. And there are good studies that show if you infect mosquitoes with this, they then carry it around and they are much less likely to transmit. So here are 3 novel methods by which we can control Aedes-associated diseases. But they're not as good as the bed nets or the insecticides on walls that we use against the Anopheles mosquitoes for malaria. And finally, on mosquito-borne diseases, just to acknowledge that mosquitoes can also, and these ones are a different group again, these are Culex mosquitoes. These mosquitoes can, in some situations, pass on infections from wildfowl or animals to humans. You are what is rather elegantly known as a dead-end host. They're not intending to infect you, but the fact is it can still cause you problems. Generally, it's water birds or ordinary birds. Japanese bee encephalitis, the most common cause of encephalitis, infectious cause of encephalitis in Asia. Pigs and water birds are the main thing, and then the mosquito transmits it to us. And then West Nile virus, something which, for example, is now the most common mosquito-borne infection in North America at this moment in time, would have been malaria going back. And that, again, is from birds. So these are potential issues. Vectors are a good way. If they bite you and they bite another species, if that species has got an infection, potentially this is a way in which an infection can jump species, even if you don't meet the animal. That's the point about vectors. They can travel a long way. So it's not just in people who are farmers or people who are abattoir workers or butchers. So most of what I've talked about is the mosquito-borne diseases because they're the most important, but just a few of the other ones. Fly-borne diseases. Classic one is sleeping sickness, human African trypanosomiasis. The main form of this is a human-to-human one. It's a human disease, maybe a few animals get it, but it's basically human disease. And it's passed on by this thing, the tsetse fly. Very unpleasant bite if you get it. It tends to interact with humans at river verges. If you get bitten, you can get this parasitic disease, which then migrates into your brain, causes an early form of dementia, and then you die. It's not great. The sleeping bit of sleeping sickness is people had sleep inversion. They slept during the day and they woke up during the night, or just became generally somnolent. Untreated, this is almost always fatal. And until very recently, the drugs we used to treat it had a 5% mortality rate, just the drug did, because it's an arsenic-based drug. So now we've now got much better drugs, really in the last couple of decades. So when I was training in tropical medicine originally, we were using these kind of drugs as standard of care. They've had several massive epidemics in Africa over time, where very large portions of the population, up to 50% of some villages, would catch it and then would die. The control of this is you find the cases and you treat them, and then because we've got new drugs, that's become a much lless dangerous thing to do, so we're more effective at that. And back last year, less than 1,000 cases are reported. That won't be all the cases that exist. They're particularly common in areas of conflict, for example, because control is bad. But this disease is currently right down from the over 500,000 cases that we're reporting in the 1990s. So definite direction of travel good, because it's a combination of attacking the vector, which I'll come on to, but particularly drug treatment for this form. But the other way is there's another form of sleeping sickness, and this is passed on by animals, either wild or domestic. And for those, finding and treating human cases isn't going to help you because you're catching it from the animals. And for those, therefore, you have to go for vectors. Unfortunately for us, tsetse flies are very stupid. And they think that those blue and black things on the left are really great. So if you put an insecticide on them, that deals with your problem to quite a large degree. So for dealing with this one, a lot of it's finding the areas where tsetse flies and humans interact and then putting out the traps or these screens. They see that as lunch and they die. So a good thing. And the thing about this, and it's an example of the geography of vector-borne diseases, on the left, that black line, everything to the left of that is the human form, human-to-human form, and everything to the right of that is the animal form. So geographically, they're quite distinct from one another, overlap just about in Uganda. Another fly-transmitted infection is this one, onchocerciasis, river blindness. Very common in limited parts of Africa and much less common, now almost gone actually, in parts of Latin America. It's passed on it's a worm. It's passed on by this fly on the left, Simulium damnosum, and it causes vision loss and can also cause skin inflammation, which sounds trivial, but it's non-trivial. The way we've controlled that is a combination of vector control by spraying larvicide in particular in areas where the vectors breed. That's what's happening with that helicopter on the right. It's spraying larvicide over breeding areas. And then mass drug administration using the, can I stress this word, anti-parasitic drug, ivermectin, which is highly effective for parasites. So that's the way in which this particular group of infections have begun to be controlled. And although there is still blindness due to this disease, tragically, it is going down very rapidly, and as I say, in parts of Latin America, has largely been eliminated. There are other important fly-associated diseases, and I'm just going to give two. On the left is lower. This is also passed on by a fly, actually pretty harmless, but if that worm on the left wriggles across your vision, it does cause you a certain amount of upset, unless you're very steady-nerved. And on the right, actually a much more serious disease, a serious cause of blinding, trachoma, used to be common actually around much of the world. This is another example of something which has got multiple routes of transmission, mainly touch. So it's mainly people touching their eyes and touching other people or passing it on by physical means, might be a physical object. But another way is by flies. These are bizarre flies, very common, and they feed on the mucus and they'll fly around and then they can pass it on. So here's a fly doing it just by mechanical means, is passing it on. Rather different from the other ones where the vector is actually an intrinsic part of the infection's life cycle. Trachoma, I'm glad to say, is another disease which, due to fantastic control efforts, mainly mass drug treatment, is gradually going down. So these are vector-associated or vector-transmitted infections, each one of them major causes of blindness, each one of them, and vision loss, each one of them gradually improving. Finally, the arachnids. These aren't insects. For the pedants amongst you, these are arachnids, closer to spiders. Ticks. Ticks pass on a very large number of infections. The most common are what are called the spotted fevers, tick-borne typhus and other spotted fever diseases. African tick-borne typhus is the most well-known one. The clue's in the title. It's in Africa. Have a guess which country Rocky Mountain spotted fever is in. North America, obviously, Queensland, tick typhus, and so on. So there are lots of variations of this. They're all passed on by ticks. It's a type of bacteria. Generally, if treated early, for most of these, it's a relatively mild disease, but causes a fever and a rash, and you treat it with antibiotics. There's a variant of this, which is called mite-borne typhus, which is passed on by those tiny things I showed on the head of a pin earlier on. It's another arachnid, and that's the form you tend to get in Southeast Asia. It's more severe, actually, and people who get it who tend to be crawling around in the various jungle areas. And finally, and importantly, on these, Lyme disease. Lyme disease is the one disease of this form which is common in parts of the UK, relatively common in parts of the UK, but it has quite a distinct geographical range, actually. This is passed on by ticks as well, and very much more common in parts of North America and some parts of Europe as well. This is a tick-transmitted infection, mainly from people. You're not going to get it in an urban environment. You'll pick this up in wooded areas, particularly where there are deer or other species. It's other mammals that may have it. The thing which people worry about with this, if treated early, Lyme disease is usually relatively straightforward, but there are some more severe forms of Lyme disease. They are serious diseases, to be clear. The minority of people who've got Lyme disease, and most people who think they've got Lyme disease haven't got Lyme disease. It's overdiagnosed to some extent, but it is worth treating. And even in advanced cases, the great majority of people can be treated very effectively. And there was a very nice study for those who are interested in this, because I think this is a worry. A lot of people know people who've had Lyme disease. It's quite a common disease to be aware of in the population. It's worth looking at this. This study compared people who'd had neuro-Lyme, which is the form that goes into the brain. That's the most severe form of Lyme, to people who had not. They'd all been treated, and they compared their long-term outcomes in terms of education, in terms of what they could do physically, in terms of various things. Basically no difference between them. So provided you find it and provided you treat it, the outcome for this disease is actually, if treated, very good in the great majority of cases. There's a slight increase actually in people being married if they'd had neuro-Lyme, but I don't think that probably is cause and effect. That's a difference between causation and association. And an important one in the rest of Europe, tick-borne encephalitis. This one is worth being aware of. If you're going to go hiking in woods in Central Europe or Central Asia, it is worth getting vaccinated. Very common, passed on by ticks, very effective vaccine, not massively long-lived, but if you're going to go on a holiday, be aware of this one, because it's an easy disease to prevent, not by stopping getting bitten by ticks, which is tricky, but by vaccination. And if you do have a tick, just take it off. You flip it up backwards and you pull it out. That's basically, and shove a bit of antiseptic on it. So the quicker you can do that, the less likely you are to get infected with any of these infections. So in summary, we have a bunch of very important diseases, and the control of vector-borne diseases, which are common, varied, and can be very dangerous, relies on really three pillars, and the ratio of them depends on which disease you're talking about. They're very highly concentrated geographically for most of them, and that concentration is to do with where the vector lives, naturally. And the three ways we can attack them are attack the vectors by a variety of different methods, and I've talked in particular about malaria, but also some of the others. Killing the infection, so if you've got an infection, the vector can't pass it on, and you can also treat people, so early treatment. And for some of them, I'm glad to say, vaccines. And the biggest triumph in the last 10 days is the malaria vaccine. So an important group of diseases, some getting better, some getting worse, but that is the first of the 5 routes of transmission I'll be talking about for the rest of the year. Thank you very much.
Will the scientific advancement made here be transferable to other insect-borne diseases so that those diseases can be eradicated?
Thank you. Well, first thing to say about the malaria vaccine, absolute triumph. And a lot of people, including me, were fairly sceptical that this was going to be able to get to this stage. So, I think really something to celebrate. But I don't think anybody who understands this vaccine thinks it is powerful enough to lead to eradication. So this is very useful for stopping people dying. it will not give you anywhere near enough control to lead to eradication. So the first thing is we need to curb our enthusiasm. We need to be aware this is a powerful tool, but it's not alone going to do a huge amount. But what it has demonstrated, and I think there was a lot of caution about this, is we know we can get lots of vaccines for viruses. Not all. There are many viruses we don't have them for, like HIV, but many viral infections and many bacterial infections, but we really don't have many vaccines against parasites. Here's an anti-parasite vaccine against a disease which is very common, and that's a real step forward. But I think we should take things one stage at a forward. This is a solid step forward, but this will not, I'm afraid, lead immediately to the elimination of malaria as a major threat in Africa and Asia. It's still going to be there in parts of Latin America.
Thank you very much. The second question is, are arthropod infections, e.g. from ticks and mites, harder to tackle with public health initiatives than true insect-borne infections like malaria?
Thank you. So I think what the things like ticks and mites are harder to deal with is stopping them biting you. They're basically in the environment. If you go to them, if you go to their habitat, they may well get you. But we do have effective treatments for the majority, or we have effective vaccines, as we do, for example, for tick-borne encephalitis. And the three pillars of public health are anti-vector, treatment, or vaccine. Ideally, of course, all three. But for many of these ones, you're either dealing with treatment, Lyme disease, for example, or dealing with prevention via vaccination, tick-borne encephalitis. But dealing with the ticks themselves is harder. That is absolutely right.
And there's been a group of questions on this topic as well, and you did touch on it. It says, given the current concerns regarding climate change and the increase in global temperatures, do you think this will cause a migrational change to vector-borne diseases and their ability to spread throughout a community?
Yes, thank you. So the climate change will lead to many vector-borne diseases moving around. It will increase the range of some, and we talked about Aedes. I think that's going to increase its range. It may actually decrease the range in some other areas. So it may actually lead to a geographical shift. There may be some areas, for example, that had heavy rainfall, which will have less rainfall, which is less good for the mosquitoes. So it's not invariable that climate change will be good for a vector-borne disease. In some geographical environments, it may even be bad for it. But overall, it's certainly going to move them around, and I think it's likely to move them further out from the classical tropical areas, out further north and further south, because it's going to allow for warmer and often rather wetter environments.
And the last question is quite a big one. So this is a question about whether on a worldwide scale, when you're looking at all the sort of diseases and medical problems in the world, are insect vectors of most concern, or ought we really to be looking elsewhere?
I think that if you live in an area where malaria is your most common cause of children dying, a vector-borne disease is absolutely the most important infection. And if it's your number one thing, you're going to want to drive that right down. If, on the other hand, you're living in central London, vector-borne diseases, other than when you travel to a vector area, are unimportant. Now, I happen to work in the Hospital for Tropical Diseases, where lots of people with vector-borne diseases come into London, but they didn't catch it in London, they caught it in other places. So I think it depends entirely where you are, and that's the reason that I wanted to concentrate on this point about geography. If you go into an area where there's a lot of vector-borne disease, you may well catch it. If you stay in an area where there aren't vectors, then you're not likely to. It's very geographically focused, so it depends where you are.
Thank you very much. We just need to make an announcement that this evening the exit from the lecture theatre is at the back, not at the front. But in the meantime, can we just thank Professor Whitty for another fantastic lecture? Thank you.